SNARK Chocolate, a show about ZK products where we break them down with rich flavors and sweet insights. My name is Omer, and I'll be co-hosting this episode together with Queenie. Today, we're thrilled to be joined by Lukas Helminger, CEO and co-founder of Taceo, and Lukas Gotz, product lead and co-founder at Taceo. This one is going to be cryptography heavy, and we can't wait to start. Lukas, it's great to have you here.
Thanks for having us.
Thanks for having us.
Could you please introduce yourself and how you came to work on Taceo?
Sure. So I first got into cryptography around the age of 14. I've read the book called The Code Book by Simon Singh. But actually from like the age of 14 to 20, I focused more on becoming a professional cyclist. And this didn't work out at all, so I decided to pivot and turned into my passion for cryptography and study mathematics. During that time, I also had my first few startup ideas. One was a nightlife app where we were able to help find friends at bars. People were scattered all over town. You want to know where are my friends in which bar. Basically, very much motivated by my own interest at that time. Another was a variable to track jump performance in volleyball, inspired by my girlfriend that played volleyball at the time, and I saw that they don't have anything to measure their physical activity during a match. And things got more seriously than in around 2019, where I joined the Gotz University of Technology, where I started my PhD, and I focused on multi-party computation, so short MPC, and privacy-enhancing tech in general. Also working in EU-funded research projects related to GDPR and data markets. And actually, that's where most of the team that work now at Taceo I first met at this research lab at the Gotz University of Technology. And in really at the beginning of the pandemic, the Austrian government reached out for help to us for building a privacy and preserving protocol to combine data such they could better monitor the crisis. And we just built this prototype in a few weeks, and which would scale to a nation level, which sparked the idea that this technology, all this privacy tech, we are now able to scale this to really industry large use cases. And at the same time, we also saw that the first ZKVM projects like RISC-0, it seemed really very ambitious and crazy what they're doing. And we thought why not take a similar approach for MPC? And that's where basically the ideas for Taceo combined and really manifested.
Yeah, so my journey started basically more than 10 years ago when I realized Bitcoin is becoming a thing. Actually, it was right after the Mt. Gox hack. I got interested and in Bitcoin back then and started investing. Thing was just 2 weeks later, I made 50% loss on my investments already. So I kind of used to these current downturns we see in the markets. I'm quite chill, I would say, being that long in crypto and going up of all these ups and downs for the last 11 years, basically. Started my first company end of 2017 in that field. We started to, as a team, as a company, invest in the space, but also supported our investments with dev power. So we closely worked on Terra ecosystem back then. 4chain was a big thing for us. Phantom and other layer ones. Quite early involved in DeFi protocols, and that was also one of the reasons we then built our own DeFi protocol back then. Was basically an automated investment portfolios on-chain, so smart contract based. Try to capture the best yields for the people investing there. But already back then, I realized, okay, this is kind of an issue with all this data being public. So we have built these strategies on-chain, and as it is, everyone can see how the strategy works. Everyone can copy the strategies. So we were kind of blocked to build more sophisticated strategies there. The other option just would be to do it off-chain, but then we would kind of lack the trust we got from smart contracts and on-chain logic. So already back then I saw this is an issue, and we don't have the deck at hand to solve this. And yeah, at a local crypto event back in our hometown, I met then the other folks from Taceo, and we kind of matched and realized, okay, we can build something together. We can bring this confidential compute capabilities together to blockchains, and this was kind of the moment I joined the team, and yeah, now responsible for this entire product aspect of the CEO.
Okay, so the first speaker was Lukas H, and the second speaker was Lukas G, just to clarify. Now guys, Taceo is known for working on co-SNARKs. I think a good starting point would be to explain what are co-SNARKs.
Sure. So basically, a co-SNARK means you generate a SNARK inside an MPC protocol, like MPC, multi-party computation, for those who don't know. So the main difference to a single proof setup is that in a co-SNARK, you actually share the witness, the secret witness of the SNARK generation with a set of MPC nodes. And while doing so, you kind of keep the privacy property of the SNARK generation. So imagine compared to a local SNARK generation, user can still now outsource the SNARK generation to a network of nodes, while still have a similar trust assumption as doing this client side. And we see this now enabling two main use case areas with co-SNARKs being at hand now. One is the field of private proof delegation. So as mentioned earlier, as a user, you can now decide on, okay, I produce the SNARK client side on my device, or I outsource it to a network of MPC nodes which produce the SNARK for me. This is kind of the obvious use case we see, and we already see quite a heavy demand in the field of ZK apps and ZK protocols, because many times user hardware is just limited in resources. And instead of waiting 30 seconds or a minute in order to get the SNARK produced, they can now outsource it to a network where it's done in usually a few seconds. And the other big area, which we think is even more exciting, is called private shared state. So contrary to the proof delegation, where we have this one user is outsourcing to a network, in the private shared state setting, we have multiple users which provide private or secret inputs to a network, and this network can then compute on those inputs. So maybe take a simple example of voting. We can collect multiple private votes, and this private shared state, which is then formed, can be computed. We can compute who is the winner of the voting, for example, while still preserve the privacy of all the inputs given by the users.
So for this episode, we've done something new. We actually went before and asked different members of the community about what questions they would like to ask. And one surprising question that we got is about the differences between the MPC setting of two parties and a multi-party setting. Are there any differences that you can highlight between these two settings when it comes to co-SNARKs?
Sure. Generally, like co-SNARK is the concept of combining MPC and ZK as a ZK proof system with an MPC protocol. And you're quite flexible which proof system you can match with which MPC protocol. And like as most listeners know, there are different MPC protocols, like you mentioned, two-party protocols, three-party protocols, or even like n-party protocols, where you have like hundreds of nodes. They all differ in which trust assumption you give to the MPC network and what the performance is of the actual computation of the co-SNARK. So we are seeing that like the most performance setup for co-SNARKs is a three-party setup in most of the cases. Two-party is most of the time not as efficient as three-party, and also doesn't give you more guarantees than the three-party setup.
Can you share maybe more examples for when one use case is going to be better than another in terms of number of parties or other parameters?
In MPC, there is this rule of thumb that the communication increases with every party that you introduce. So going beyond a handful of nodes, most of the time increases the communication quite heavily. So you stick to a lower number of MPC nodes if you want to have a high efficient use case. There is, however, the case where the computation is very lightweight, then you want to decentralize for some certain use case the MPC network further. And as an add-on, a two-party computation makes most sense if there are only two parties involved with their data, if it's really peer-to-peer between two data. For example, a prime use case would be private set intersection. So if we want to find out who are our common contacts, for example, for a signal, that without sharing the whole contact address book with the signal servers, this would be a prime example of a two-party protocol.
So you previously mentioned that this is very modular, the stack. You can take any ZK, any MPC. I guess you do need to pay in some way, right? And maybe pay more when you choose one ZK or one MPC over another. What are the new bottlenecks that these systems face?
Yeah, in general, like you said, we can combine them, but there are different trade-offs. And currently, SNARKs, so elliptic curve-based commitments, are better suited for co-SNARKs than hash-based commitment schemes like we're seeing in STARKs. So this additive homomorphic property of this commitment helps a lot to reduce the communication in the MPC protocol, which essentially for the use case of private proof delegation leads to little to no overhead compared to the single server setting. So you are facing the same performance than with, from ZK SNARKs. If you're talking about private shared state, there is a new bottleneck introduced, which is the witness generation, which gets little attention, except maybe in the hardware space of ZK hardware, because usually it's orders of magnitude faster than the actual proof generation. For those that are not too familiar with witness generation, it's basically where you do the program execution before you then actually do the proof generation. And for private shared state, to have those privacy guarantees, you have to perform the witness generation in MPC. And the witness generation allows for any program, so it must be really general purpose. So to make an efficient witness generation MPC, this is a new design space or new issues and new research problems you introduce here.
So you just described how to take existing ZK proofs and compile them into a co-SNARK based provers. Are there other ways to do it? Or is it going to be just a feature of different ZK protocols? Now there's going to be, let's say, a lattice-based prover, and you can build it in a way that's also going to be secure for co-SNARKs. Or is it going to be also possible to build something that natively is like a co-SNARK and have some other benefits? Or I don't know, starting from MPC, let's take MPC and find a way to add to that some kind of a ZK computation that's happening as part of the MPC.
Yeah, this then, in academia, you would probably call this audible MPC, where you don't start with the ZK proof system, but with the MPC, and you want to make this audible to some third party that was not part of the MPC computation. The setting that we're focusing is mostly like on-chain use cases where you need some succinct verifiability to make the use case interesting. But one really interesting research area which we're kind of starting is to look at how would you design a ZK proof system today with in mind to having like that make it perfectly suitable for co-SNARK. So like really starting from scratch again and seeing like if you would build a ZK proof system in the mindset of like it has to be fast in MPC, how would this look like?
I'm just curious about like what inspired the creation of this structure because I feel it's super innovative and unique. Yeah, just curious about the stories behind.
Yeah, so I think we were quite open to any technology, like from a cryptographic standpoint, how to implement the thing we wanted. And what we see in the market was this: there is the need to handle private data and compute on this private data in an on-chain context. And with that goal in mind, we were quite open if it's now MPC, ZK, FHE, TEs, whatever solution, which probably all of them goes in the same direction and try to achieve the same result. But only going through all of these categories and the DEC team really working on these technologies back then at university, we realized actually this combination of MPC and ZK is kind of the perfect fit, which gets us all these properties we want to see in order to get a form of confidential compute in an on-chain setting. MPC only would lack this verifiability. ZK only doesn't enable you to collect multiple inputs and compute on them. But actually combining those two, we get the properties we wanted to see.
Got it. And can I say actually, both MPC and ZK applications nowadays, they should consider leveraging Taceo?
I mean, yeah, that would be great, of course. I think it really depends on the actual use case and what you want to achieve. We see a lot of those ZK applications where ZK really stands for zero knowledge and not using ZK for succinctness reasons. We think that is, from that side, we see a lot of demands because these are types of application which face these client-side hardware constraints, which face this bad user experience of long proving times on client side, and they heavily benefit from outsourcing this to a co-SNARK network as we offer. On the other side, those MPC projects, I don't know, don't think there are that many which are really built MPC applications as of today, but still, I think they need this form of verifiability when they want to interact with some on-chain logic. Otherwise, the MPC computation you perform in an off-chain setting would be just an oracle to an existing blockchain, because the output you write back to the blockchain would come without any verifiability. And so you would trust the MPC network not only for privacy reasons, but also for correct execution of the code of the application. And with the co-SNARK, this is actually achieved that you can still verify the integrity of the computation of the MPC network. And only if the verification is successful, you then update the state on the layer 1 or layer 2.
I see. Then how to understand the easiness or difficulty to integrate with Taceo? For example, if a ZK EVM project or a ZK DID project, they already built their own stack, then how easy it is to just integrate with Taceo?
I think it's quite straightforward. So if there's already some existing ZK circuits written out, you could just leverage our existing libraries. So we build a library for Circom. We call it co-Circom, and the same for Noir, co-Noir, where you just take your existing circuit, you compile it down, and you can run this existing circuit in a co-SNARK setting. So no changes are needed there, and just use the existing infrastructure which is available.
Yeah, so because you currently have Circom and also Noir, so you probably have some plans to support more prover system in the future?
Yeah, so like Circom and Noir are the front ends how you can write today collaborative SNARKs. For the actual proof of systems, we already support like Plonk, Grove 16, and UltraHonk. And like with Noir, it's very easy to add new proof systems. Like Noir was designed in a way that it's backend agnostic, which means like you can add different proof systems in the backend while still having the same front-end language. So for expanding to new proof systems, we still can rely on Noir, this very popular zero-knowledge domain-specific language, which is really picking up right now. And this is the one thing that matters to devs. They need to be able to write their circuits, their programs in a language. Whatever used in the backend, they don't really care. And Noir allows us to like easily extend this with other proof systems.
So repeating it in my own words, there is a product, let's call it Taceo for now, and this product allows you to, as a developer, to produce co-SNARKs. You have a front end where you use industry standards like Circom and Noir, but you modify them accordingly. And there are backends, and here you have the provers, where you are already supporting a few provers. And I guess you're going to add support for a few more in the future. Is that kind of like a good way to capture product?
I think that's a good description of it. Maybe one thing missing. So we provide these libraries like co-Circom, co-Noir, so that people can actually write their own co-SNARKs application. But the second important thing is also some network for actual execution of the requests. So this is what we currently spinning up, that people can write the applications, but also have some place to actually execute these applications in a network. I mean, they could do it on their own, obviously. So they could spin up their own nodes, their own network. But this is usually something people don't want to do. They just want to use existing infrastructure, and that's what we offer, spinning up this decentralized network of co-SNARK nodes, which providing the compute power.
Oh, interesting. So you also provide the infrastructure as an option.
Exactly.
And this can be like the MPC nodes can, how many this can be? Like can go up to 300-400?
So like we provide the protocol, actually like the ones that executing the computation then are node operators. These are like, could be ZK proving markets, this could be like professional node operators, validators, and like we'll have a pool of them, and where like it comes down to which MPC protocol you're using, how many you have to choose for one job, like how many are get selected for at one time, and you choose out of this like large pool of providers.
Oh, I see. So it is kind of a network that is part of the product, and as part of this network, you can become an operator running a node, and it means there's some kind of like a mechanism how to get this network to, incentives and so on, how to get this network to operate correctly and securely, right?
Exactly. And there needs to be some on-chain logic involved from our side to actually make this node selection working. So yeah, that obviously not always the same node should be selected. Not one node provider should be in charge for computing this entire job. And also some market mechanisms which will be implemented, so to offer the cheapest price in the end for the job requester.
Okay, so in terms of a roadmap, what currently exists? Like, is it live? Is it based on some like existing blockchain infrastructure? What are you planning to work on next? Adding more provers? Like, what kind of like the where the users are coming from, so on.
Yeah, maybe I can touch into the network roadmap. So we are close to actually launch the first production-ready network, which will be dedicated for private proof delegation. So planned for end of May this year. So from that on, projects can just leverage this existing network and outsource proof generation to the network. We will start with a couple of selected node operators, which doing this professionally already, and later open it up to a broader market that everyone can provide compute resources to that network. There will be another launch quite just a few weeks after, which is not yet announced, but with one big partner of us, we're going to launch another network. And yeah, later this year, also tapping more into this private shared state application. So we already see some projects playing around with our tooling to build private shared state applications, which is quite exciting for us to see and also to learn what people imagine in terms of use cases. And yeah, that's something we definitely want to push and also to provide the right infrastructure for execution then.
From the dev experience, and I have to admit that I haven't tried it myself, the product, but hopefully soon. So coming from this kind of like background, is this going to be something like you can take an existing Circom circuit or like Noir program and just co-SNARK it, or is it like going to be something you need to build with, or you are adding something to this like API or languages that allows you to express something that should be now co-SNARK?
Lukas?
Yeah, so for private proof delegation, it is, as you said, like you can't use your existing circuit, just throw it down our library, and it will compile down to this collaborative SNARK, which you then can use for private proof delegation. So no need to change anything here. If we are thinking about private shared state, there's you have to write the programs with the business logic that you want to have as a private shared state, like which variables do you want to keep private. You have to write those programs with that in mind. So typically private shared state applications would be built with already co-SNARKs in mind. For existing projects that want to leverage private proof delegation, it's just like using your existing circuit and compiling it with another toolchain.
And maybe to add here, it's not there yet in our library, but will soon come. So when you write your private shared state application, for example, in Noir, in the end, this will compile down to one artifact will be the co-SNARK circuit you can then deploy on the MPC network. The other one will be the on-chain smart contract. So you can write your usual application in your preferred language and get those two artifacts out of it, and you can just deploy it on whatever chain and on the co-SNARK network.
So another question I was curious about is monetization of all of this, specifically this product. All right, so Circom, Noir, they are open source libraries, anyone can use them. I guess the monetization coming from the network in a way, right?
Exactly. Yeah. So we as you said, these Circom, Noir, these are open source. We also open source our libraries built on Noir and Circom. We are super happy if other projects just take it and extend it. I think we can also benefit a lot from that. And where we see then kind of the monetization of this whole product is, as you said, is in the infrastructure, in the networks. Every time compute resources are requested from the network, we charge a fee. I think that's kind of the basic model for now. In the future, we think the most valuable applications in an on-chain context will be built around private shared state. We hope that a lot of those applications will exist, holding their private shared states in the Taceo network. And what's actually interesting is when these different applications start composing on various private shared state instances. So, for example, when a private DeFi application is tapping into a private social application for KYC reasons. So then two instances of private shared state would interact with each other, would compose on their private shared states, and we think that's actually the really, really interesting part of this whole product we envision.
Since Lucas already talked about some applications, you just mentioned private share states. Would love to learn more interesting potential use cases on Taceo. I saw on the website you mentioned several cases like DeFi, like AI, and even MPC ZK So would you like to share some exciting ideas here with us?
Absolutely. So yeah, for private proof delegation, we think kind of any ZK app out there or any ZK protocol would heavily benefit from using the co-SNARK network just to improve the user experience for their users. So as you mentioned, ZKDLS is, I think it's a hot topic right now. A lot of projects are approaching this, and we already see some real world adoption using ZKDLS protocols. Outsourcing proof generation to the network would definitely increase the overall experience users face. Plus, we can even extend what types of proofs those ZKTLS protocols actually can generate. I think nowadays they're sometimes quite limited, not only in proving time, but in overall what types of proofs you can generate and how sophisticated these proofs are. Having now these beefy machines in a network, you can be more creative and can definitely build more sophisticated applications. Same is for ZKML. I think that's another interesting area. We also, when talking to teams there. And also ZKML. So similar issue, you can't run the model inference client side, and while proving it, we can outsource it then to the network and still get this whole experience. Lukas.
Like, if we go beyond private proof delegation, I think there are some obvious private shared state applications that people wanted to build for some time now. They didn't know that this would be called private shared state, but they had like the problems that hold them back for actually deploying it, which it turns out it was private shared state. So for example, dark pools, where you can match orders in a private way, but in an on-chain context without having a trusted operator. And we're currently seeing this doing, like, for example, Renegade already. Then like the next big steps are like private while combined with stablecoins. Like if you, for example, as a company want to pay your employees on chain and want to use a stablecoin, you have to get some certain confidentiality to make this happen. And private shared state is exactly where this compliance feature, you can like catch the, or like you can make this compliant while still having privacy. Another similar, or like in the same bucket, is RWA tokenization. Like if you want to have these assets on chain, most likely you need some sort of confidentiality that like makes sense, that the business makes sense, and that's where private shared state will be very helpful, as well as on like on-chain games. This is the classical example of private shared state, like hidden informations in a chain, in an on-chain game like poker, like replacing the dealer with untrusted nodes, but still can be verified that like nobody has cheated.
Lucas, could you please extend a little bit on how to keep compliance while still have privacy?
Sure. Like you could probably do a private stablecoin with ZK only, but once like you want to have some compliance, you either with ZK disclose, like you have like a viewing key, for example, that you give some regulator and then they see all the transactions you have made. Or you can leverage private shared state and make this controller that like looks that everything is compliant in a shared way, like in a private shared way, in an MPC protocol. Like you're distributing this controller, decentralizing this controller that can then monitor that everything is like compliant, but without seeing any details of the payments that are going on. But the controller can still be sure that, like, for example, a transaction was never hitting an address that was blacklisted.
Cool. I think that's super important for scaling privacy. I'm curious, can we also build private share state, this kind of application, using other MPC or ZK protocols?
I think you can use other MPC or ZK protocols as well, but with a different kind of assumptions you get. So if you just have this MPC protocol without verifiability, as said, you can use it, but you kind of lack then this verifiability of the computation. You don't know if the computation run by the MPC protocol is actually correct. Obviously, there are other approaches to get to confidential compute, which is probably this umbrella term we're all talking about. You can follow this FHE route, which also is a form of confidential compute, where you could generate a form of private shared state in, or you go back and relying on TEEs for doing so. But we think as of today, this match between MPC and ZK gives you kind of the best out of multiple worlds to get the best assumptions, and also in terms of performance, it's still highly performant to run these computations, which a lot of people are surprised to hear. But we've shown it, for example, with Vault, that you can run really huge applications in an MPC setting. So I think that's something to consider, and we can show more use cases, more applications soon.
I'm glad that you mentioned performance. I think it's always the case when people are talking about MPC, ZK, like their top concern is about performance.
Yeah, definitely. Like this is what we're hearing from the market. And while we focus a lot on performance, so this goes also back to like our time back at university, where one of the main research areas we did is like optimizing hash functions and encryption schemes like Poseidon for the dedicated setting of ZK or MPC. So this is like really what we care about, and fortunately also the market values it a lot.
So I wanted to squeeze a couple more questions, unrelated, but I'm gonna share them together. So one is about your take on TEs, which is another technology, hardware security that might help. Are you working with TEs? What's your opinion? Second thing is about academia. So I guess one of the benefits of working at this kind of like bleeding edge is that, everything you do is like, by definition, it's an innovation, right? So you can see it from your tweets, Lukas, right? You say something, usually it gets quite a lot of responses. And I'm curious if you guys are also like kept kind of like your roots coming from academia. Are you still kind of like involved in some academic research around these areas, collaborating with the different teams, working worldwide on this problem of collaborative SNARKs?
Yeah, like let's go first into the question about academia. So we're still very much rooted in academia. Like one of our co-founders, Christian, he's still a professor at Graz University of Technology, and that's where we try to push the topics that are relevant for co-SNARKs in academia. So one ongoing work is in the area of MPC lookup tables. So this is quite similar to ZK lookup tables, which are quite popular, but not that popular in MPC, and which again go into this like new bottleneck of witness generation, where they really can help if we have efficient MPC lookups, which we can share more about at the next ZK Summit in Toronto. And currently we are really trying to get a research effort out of co-SNARKs, so collaborative SNARKs for these hash-based functions. So we're collaborating with different researchers around the world to have more efficient or even the first real construction implementation of a co-SNARKs.
Yeah, maybe to your question regarding our take on TEs. So we think TEs should be used complementary to other solutions. I'm not sure if relying like a persistent private shared state just on TEs is the way to go, because there's kind of a huge honeypot to capture there if you can access very sensitive data held in persistent private shared state. As we approach it is to investigate how we can combine now MPC with ZK, like co-SNARKs with TEs. So it's now kind of matching all those privacy enhancing technologies together. But we think that actually makes sense to run a co-SNARK node in a TE. So even now then with let's say a free party MPC setup run in TEs, you get really high trust assumption, because you would need to break the TE, plus you would need to make a collusion between multiple nodes. So that's something we are heavily looking into. We also see that there's not much overhead added there. So in terms of performance, it's also quite nice to combine those. And ultimately, this gives you a really, really powerful combination of various technologies.
Okay, so as a final question, we have a question we ask all of our guests, which is to name a project you are bullish about. Lukas, Age, let's start with you.
I'm quite interested and really rooting for the success for Filewars. So I think like in our everyday operation as a tech company, we're too reliant on centralized tech stack that is also like really spying on us and like extracting a lot of value out of us. So yeah, seeing such an ambitious project like Filewars, I would be really happy to use it.
Yeah, and I would say probably I like what Penumbra is doing. I think that's a pretty cool approach. I think that's definitely needed in the space to get more privacy in your trades. I think they are going in the right direction for doing so.
Excellent. So with that, Lukas, thank you so much for joining us today. It was great to learn about collaborative SNARKs and the ecosystem that you guys and tools that you guys are building around it. For those who are interested to learn more, we are adding some links in the show notes. And that's it. Thank you again. Thank you, Queenie.
Thank you.
Thank you.
Thank you guys for having us.